Welcome, everyone. Sorry for the delay of 2-3 minutes. So welcome to our last machine learning seminar at the University of Auckland for this year. And this event is actually co-organized with University of Waikato. And I'm really happy to have the guest from Brazil, Rodrigo Mello. Welcome. And he will be introduced by our Heitor Gomes from University of Waikato. Welcome, Heitor, and please introduce our guest.
Okay, thank you, Katerina. So I will now proceed to introduce Rodrigo. So Rodrigo is Associate Professor at the Institute of Mathematical and Computer Sciences at the Department of Computer Science in University of São Paulo. He obtained his doctoral degree in 2003 from the University of São Paulo. His research interests include machine learning, applications in dynamic systems, time series analysis, and also data streams. And then I think I will wrap it up, and then I will leave it to Rodrigo, so he has a lot to tell us about. So thank you, Rodrigo, for joining us. Thank you, Katerina, for organizing the joint seminar. And please, Rodrigo, whatever you want.
Oh, first of all, thank you very much, Heitor. Thank you very much, Katerina. It's just like an amazing opportunity to present and introduce a little bit about my work, what I've been doing, like I'd say at least like for the last 8 years in that particular subject. So we're going to discuss a little bit about the estimation of the complexity of supervised learning algorithms. I'm not sure if you guys can see my screen or
not yet.
Is it okay?
So you can share now. Yeah, you can share now.
Okay. That's great.
I guess to make things simpler, I would suggest that all questions come at the end, because it will be much more difficult to interrupt you all the time. It's not the same setting as we are in the same room. So when you can easily watch the audience. So I suggest that all the questions come at the end, but you feel free, the audience can write questions while you're talking. Thank you.
Okay, so guys, probably you can see my screen now, right?
Yes.
Yeah, that's great. So I'll talk a little more about this subject I've been working for the last 8 years at least. Again, thank you very much for having me here. So just to start, we have the statistical learning theory is a foundation that brings proofs, theoretical proofs, especially to ensure learning bounds for algorithms like KNN, support vector machines, J48, C4.5, CNNs, etc. So if you guys have like any interest in proving learning for a particular scenario or particular algorithm, that's the way to go. So you can take advantage of all that foundation to prove learning. And that foundation, I'd start with this very important concept, which is the concept of generalization. So generalization means that the difference I have in my empirical risk, which is the risk measured on a particular sample, is not too far from the risk, the expected risk, or the risk when I have access to all possibilities for my problem, from a particular problem, a problem of interest. So in that scenario, it comes the generalization concept, here represented by G. So if you guys understand, I think it's easier to understand this concept if you think, for example, about people studying something. So someone could study like machine learning, for example, or any other subject, and we could apply some test on that particular person, and we could measure the risk or the sample error given a particular test. Of course, considering that such a person is going to come up with a model here referred to F. And of course, we expect this sample error to be a good measure, a good estimative for the expected error, which is here represented by R of F. So this R of F is the same as, what if I had access to every possibility for my problem? What would happen with my model if I tested it on like the universe of all possibilities for my problem? So what I expect really is to have like a very good estimation given by my empirical risk, of course, approaching as much as possible the expected risk. So just to have this picture, consider I have like those dots, those black dots over here, which were collected, I don't know, after analyzing a given experiment, or after, for example, after could be like any experiment. Probably, let's say we had like a car, and we are measuring the distance of that particular car moving from my house to any other place. So I have this distance a long time, for example. So I could come up with two different models over here. One overfitted model, which is of course this model that's just so perfect, and its empirical risk or error in my sample is 0. And I could have another model, which would be this linear model over here. That has like somehow, that makes like some mistakes. It's not like as perfect as this polynomial, like, I don't know, like 5th order polynomial function or whatever. But it has like, it provides a fair solution for my problem. Of course, the problem of this concept of generalization is going to be assessed when I have like more black dots in the future. So considering I will have like access to so many points later, what is the best model for my particular problem? If this like high order polynomial function somehow overfits data, of course, when I receive more points, actually my empirical risk, that's 0 here, is going to be like very, very large, because points will be somehow far from my function. And if I expect my linear function to be a good function to represent my problem, here a regression problem, but could be a classification problem, of course, more points would be like somehow a little far from my linear function, but not that far. So my point is, we can measure the empirical risk on a given sample, but somehow we should understand how my model F is going to behave if I have access to every possibility for my particular problem. That's the foundation for machine learning. So I come up with a very nice model, but what happens if this model doesn't work when I receive like unseen observations, unseen data? So that's a main point about generalization. So what I want, and what the statistical learning theory wants, is a bunch of functions f, like f1, f2, f3, f4, and all of those providing a very good generalization. So after having like a bag with lots of functions, all of those with a good generalization level, I could select the best from that particular bag. And the best from that bag is going to be like my solution, or my, hopefully, the best solution for my problem. As you guys might see over here, what happens if somehow I choose a very over-complex bias, over-complex learning bias? Of course, an over-complex learning bias means that I will somehow I will select, or at least give the chance of selecting a classification function or regression function from a very large space, We call this space learning bias or space of admissible functions. So if I have like such a very large space, of course, I have like a high probability of having a very complex function inside it. That particular function could somehow overfit my data because it's so complex that during during all learning iterations, I could somehow converge to this best possible function, and that would somehow perfectly represent my data set. But what happens when I receive more data, unseen examples? Most probably, I will fail like miserably. That particular function is not going to work most probably, just because somehow I gave the chance of selecting a very complex, over complex function from my space. Okay, so this is the foundation. In that, like from all that theoretical background, this guy called Vladimir Vapnik, he decided to use the law of large numbers, or actually the uniform law of large numbers, to actually somehow he was just interested in proving learning somehow. So he came up with this idea. I think I could share my whole screen now. I think it's going to be just like more fun. Let me try. Sorry, guys. I think it's here. Probably you can see. I'm going to open like a terminal over here. You guys can see I'm just using Linux, no problem. Yeah, I think I'm going to show you something over here. When I see this law of large numbers, there's something that just gets my attention, you know. I've got like somehow I'm just measuring a sample average over here. And here I have the expected value of a given random variable. So this law of large numbers measures the divergence or the absolute divergence I have from my empirical average or my sample average, and how it is different, or how far it is from my expected value. So that's the whole foundation behind the law of large numbers. And what is interesting here is, if I consider my empirical risk in this place, and if I consider my expected risk in this second place, I could understand how distant both risks are from one another. I could somehow, let me share my video once more. Sorry, guys. I'm just using my hands or whatever. So somehow I want to understand if my empirical risk is approaching my expected risk. That's the whole idea here. And Vapnik just decided, why not? I could take advantage of this and study how my empirical risk approaches my expected risk. And something quite interesting came after that. Let me show you here. I think this is, I know we have like probably a fair amount of time, so there's no big deal. I'm going to code something for you over here. Consider we have like this variable, which is like C of I, and this is going to be defined in a range from 0 to 1, following actually a uniform distribution. And consider we have the expected value of this variable. Of course, this expected value is going to be like 0.5 because it's a uniform distribution. Okay, so what I could do over here, I could just generate some random values from 0 to 1. For example, I'm going to start producing like 1,000 values, okay? And I know my expected value of this variable is 0.5. It is a theoretical value, of course. It's not difficult to understand because I'm just inside this interval. every value has the same probability, so it's going to be half. Okay, so how could I take advantage of this law of large numbers? I could just measure how distant in absolute terms this average, of this mean of a given set of values from 1 to I, for instance, is from my expected value of this particular random variable. Of course, it is important to have like some loop over here, defining I could be from 1 to 1000 or to the length of this particular variable. So here I have my absolute value. This is my inside term over here, without epsilon, of course. You know what? I think it's so nice to have this divergence like just being computed and added to a vector. So I'm going to add it to a vector, and then I'm going to plot it. You know what? I think I'm going to plot it as we computed. So it's going to be a little, different, I suppose. I think this is enough. So I'm going to open another terminal, open R. I'm just using R over here. So easy to use. Probably you guys know it or worked with R before. So I've got, maybe let's refresh. No, this is not nice. Maybe like this. No, it's not refreshing. Terrible. Maybe you should do something like this. Plot.new. Yeah. Oh, it's not refreshing either. No problem. You know what? If it doesn't work like this, it's going to work like this. Okay, so after producing all those divergences, we can see we start with a very high divergence. It starts like 0.25, and then it starts converging somehow to values nearby zero, of course, like closer to zero. So what is interesting here is that Vapnik just decided, why not take advantage of this law of large numbers to compare how my empirical risk approaches my expected risk. So if it approaches to zero somehow, it means that this divergence approaches to zero as my sample size increases. So my sample size is going like from 1 to 1000, and somehow it is converging to zero. And of course, here I can measure the probability of having this value greater than a given epsilon. So let's consider, here we have the divergences. Let's consider my epsilon is going to be like 0.05. So it's like 5%, okay? So how many times I have my divergence greater than 0.05, like 20 times, only 20 times, divided by 1000. So that's my estimated probability. So I have like 0.02 in terms of my estimated probability. What this means? This is very interesting. This means this right side term over here is 0.02. That means in 2% of the situations, my estimation somehow drifts away of my empirical, my expected risk, given my epsilon is like 5%. It's like 0.05. But what is the most important here? It's a complement. So if I have something that in 2% of the cases doesn't work, I know in 98% of the cases it works. So I know I will have a very nice estimation of my average considering 1,000 examples, and of course, given this average function being used. But there are some problems with this particular law of large numbers. What is interesting is This law of large numbers only works if my data examples are independent from each other. That's a very interesting point, because if you guys take all my values of this random variable and you analyze those values using like an autocorrelation function, you're gonna see there is no dependence. There is no dependence. We can see here that inside this particular confidence interval, all those dependencies of a particular value in terms of all past values are inside this interval. This means there's like almost no dependence at all. So it's not that important, that significant. So what happens if instead of that, I decide to learn something like a sinusoidal function? If I decide to learn a sinusoidal function like this, so this is going to be my function now to be learned, I will have a problem. Of course, if I apply my autocorrelation function, what I will see is something like this. There is a time dependence. And the problem here is I cannot take advantage of this if my data examples are dependent from each other. I cannot only take advantage of the law of large numbers if examples are independent. This is interesting, but it's also a problem because many times, not most, but many times we see like some studies, some papers in which people decided to relax this principle and used somehow dependent data. And that's going to be a problem. What if I decide to learn a time series using supervised learning? It's not going to work if I use the typical time domain. I should somehow reconstruct my space and come up with a different space. That's the same as a kernelization. I would come up with a different space, and on top of that space, I could learn something from it. So that's a very important subject over here. Another one, data examples must be sampled in actually here in an identical manner. By identical manner, I mean, if I have like so many possibilities, the probability of selecting any of those has to depend on the occurrence, on the frequency of those possibilities. For instance, consider I have like an axis like X, another one Y over here, and I have like a density, a probability density function, whatever. And then somehow, if I say, okay, I'm going to learn this function, of course, I have to give a greater probability of selecting a given input example X, Y, when its probability is higher. So the whole idea about being equally distributed is preserving my joint probability distribution after sampling. So suppose my joint probability distribution of my problem is like a Gaussian function. When I sample from this JPD, I should have the same behavior over here. If the behavior is different, of course, I'm going to learn something else. I'm not going to learn my data distribution of this particular problem. Another very important subject is my function being estimated must be independent from data. Wow, that's a little confusing, isn't it? Like, how can I learn something if my algorithm is going to change my starting function, converging to the best possible function to represent my data set, if the law of large numbers is only valid if my function is independent of my data? How is that possible? How could I solve that? That's not too easy, but we're going to see how to deal with that. And another very important subject This law of large numbers is only valid if and only if my data distribution is fixed. This means it is static. This means it doesn't change, that distribution doesn't change over time. Wow. So how can I learn in a concept drift scenario? I should somehow learn a given function, a given distribution, and then if the distribution changes after some time, somehow I need to forget past data and start learning over again. So what is interesting about the law of large numbers is, and many people just don't ask themselves when they are applying supervised learning on a given scenario. The only way of ensuring learning, guaranteeing bounds, learning bounds, is if all those assumptions are consistent with my problem. Otherwise, I cannot ensure it. And you know what's interesting? Just like trying to be as short as possible here. This guy over here is just empirical risk. Take a look here. It's an average of a loss function. Consider a loss function like squared error could be a loss function, or 0,1 error could be a loss function. Is it right, my classification? No error. It is wrong, 1. Right again, 0. Wrong, 1. So I just count. I just have to count how many times I made mistakes and divide by the total number of attempts, and I will have something my empirical risk. And this is my expected loss. So to have the expected loss, of course, I need to have access to my joint probability distribution of my particular problem. What is the problem? I can have access of that function if I'm working with a toy problem. But if I've been working with, for example, some continuous space, like I have like some real valued functions that can assume like any value, just impossible, but I can estimate it. And that's the point about flattening. And you know what's interesting? This is valid for a single function. This is indeed valid for a single function selected from your algorithm bias without looking at data, without analyzing data beforehand. So if you select like any function out of the blue, like without looking at data, okay, this works. But my problem is more like this. We have like an amazing number of functions inside this bias, this algorithm bias, or inside this over-relaxed bias. This is this F all is like the space, the universe of admissible functions. Here we have like every possible admission function inside it. Here I have somehow a restriction. So for example, here I'm considering a multi-layer perceptron with, I don't know, like 5 units and the hidden layer. And here I'm considering the same multi-layer perceptron, but instead of 5 units, I just decide to use like 10,000 units. This is more like a deep learning network. So of course my bias is going to be over-relaxed. So every time I relax my bias, I have more possibilities. What is the beauty about having more possibilities? Basically, I can choose from like more possibilities. But the problem is, how can I converge? What is the effort of converging if I have so many possibilities? Just imagine you guys, like 10 years ago, we had like a bias, most probably like this one. Nowadays, we have a bias much more like this one. What is the problem is that before it was easier to converge because it didn't have like so many possibilities. Solutions were like somehow similar, and you could just converge, have your time, take advantage of reading like books from your library and whatever. Nowadays, you have like Google, you have like everything is on the internet. So when you start thinking about the solution, you have like so many possibilities, and that's going to increase your effort of converging to the best possible solution inside that space. Okay, that's interesting. But so if I have all those solutions inside my bias, what should I do? What Vapnik did? Actually, Vapnik knew that this was valid for a single function. What if I have like m functions inside my bias? Let's consider we have m functions here. Okay, it is countable, but is it always countable? Don't worry, we're going to see. So, of course, my probability of selecting one particular function is bounded by this probability, is bounded by this term over here. This is the Chernoff bound. This is called the Chernoff bound. Instead of the Chernoff bound, we can use the Hoffeding bound over here as well. Probably you've heard about it before. You know what's interesting? Instead of choosing a single function from that bias, when I use an algorithm to converge using all those possibilities, I could take just the last best function and study it using this inequality. Is it going to work? No, because my function would be selected based on data. And that's a problem. I cannot use that because the law of large numbers doesn't work in that scenario. But it works if I consider the possibility of selecting the first function, f1, or the second function, f2, or the third function, the fourth, and so on, up to the nth function. So I could select any of those functions inside my algorithm bias. That is the same as the worst case scenario. I'm just considering all possibilities inside my bias and understanding, okay, what is the possibility of selecting any of those functions here? And what is the worst function of all? Actually, if you guys take a look at this probability, this is upper bounded by the sum of each individual probability. Why that? Just imagine, I could have like a function here that somehow has some intersection with another function. They are somehow similar. Is that possible? Oh yeah, of course. Assume we have a multi-layer perceptron with two hyperplanes, one hyperplane is here, and the second is here. Then I just decide, this is my first solution. Second solution, I just change the second hyperplane. What about the first? It is the same. So somehow there is an intersection, a similarity in between F1 and F2, for example. So if there is this particular intersection, of course, when I consider the probability of selecting this function and this second function, when I sum up this probability plus this second probability, I'm summing up twice this intersection, this area of intersection. That's why this upper bounds this probability of selecting like function f1 or f2 or f3 or f4 or fm. So this is upper bounded by this sum. So if I can sum on one side, I can sum on the other side. So if I can sum probabilities on this side, I can sum on this side of 2. Yeah, just like a sum from 1 to m. And that's the same as 2 times m times my exponential of minus 2n epsilon to the square. What is interesting about this is my Sheffield coefficient. What is the Sheffield coefficient function? This function measures the complexity of my bias, of my learning bias, how complex it is. It is like over complex, it is over restricted, so it's going to underfit my problem, or it is going to overfit my particular problem. And what is interesting about the Sheffield coefficient function is that there is no solution. And now this is like I just suppose we have a solution now, okay? So now we have this possibility of computing the Sheffield coefficient function. Let's see what's our approach. Of course, even Vapnik had this way of estimating the scattering coefficient function. His way of estimating the scattering coefficient function is based on the worst possible configuration of my input space. Suppose we have like 3 points, collinear points in R2. So I have just a plane and 3 points which are collinear in my space. How many possibilities or classification possibilities I have in my for this particular instance with a single hyperplane? For example, I would have like 4 possibilities. His question was, is it possible to come up with another setting in R2 from which I can get like more possibilities? Yeah, it is. If I have 3 points and every 3 points are not collinear to each other, of course, I can come up with a much more complex scattering coefficient. Actually, I can come up with more possibilities. So I have more classification possibilities. Assume we have just a single hyperplane, a binary classification. So I have negative or positive, very simple, 3 points which are not collinear. And of course, I can just cut with my hyperplane over here. I'm going to say shatter with my hyperplane over here. And all points are classified as negative. Or my hyperplane could be here and all points are positive. My hyperplane could be here and I would have 2 positives, 1 negative, or the opposite, as in here, 2 negatives and 1 positive. Or 2 positives, 1 negative, like here, or the opposite, or the complement, actually, 2 negatives, 1 positive. Or 1 positive, 2 negatives, or its complement, which is in here, 1 negative and 2 positives. You know what's interesting? If I have 2 possibilities, 2 classes, and I have a single point in my space in R2, I can classify that particular point in a power of 2 to 1. So I have 2 possibilities of classifying a single point in R2. 2 points in R2, I will have 2 powered to 2. So I will have 4 possibilities. And the worst possible setting, we call this in mathematics, we call this the general point configuration or the general point setting, in which points have always this, there is always this possibility of bringing some sort of divergence to make all triples not collinear. So if I consider like 1 point, I would have 2 possibilities. 2 points, 4 possibilities. 3 points, 8 possibilities. What happens when I have 4 points in R2 with a single hyperplane? I don't get 16 combinations. I have only 14. Why 14? Because my space R2 bounds my ability of coming up with additional classification possibilities. That's so interesting. Like my space bounds my possibility of increasing the number of possibilities I have in classifying this particular setting or set, actually. You know what's interesting here? These 2 other possibilities here are connected to the exclusive OR problem. So I would need like 2 hyperplanes to come up with these 2 additional possibilities. What is interesting here is I am bounded by the space, but if I add up more units in my multi-layer perceptron or in my convolutional neural network, what is going to happen? My scattering coefficient will increase. My bias will be more relaxed, will contain more functions, will be capable of representing more complex stuff, basically. So with 4 points, I have 14 possibilities. After that, with 5 points in R2, I will have 22 possibilities. With 6, I will have 30, and so on. You know what's interesting? My space are to bounds my ability of coming up with an exponential number of classifications. Actually, it's just possible to come up with a polynomial number of classifications after 3 points. You know what's interesting? We have like an exponential growth up to 3 points, and then it starts becoming like a polynomial function after 3 points. This number 3 is the greatest sample size that I can shatter in all possible ways with a single hyperplane. That is my Vapnik-Chervonenk's dimension, which is 3. Probably you guys heard about the VC dimension. The VC dimension is the size of the greatest sample size that can be shattered in all possible ways. If I'm considering a single hyperplane R2, that's going to be 3. But if I have like 2 hyperplanes, wow, that's actually 4. It's not just 3, it's going to be 4. And if I come up with a very nice regression on top of those points, I will have an estimation for my shattering coefficient. But you know what's the problem here? I have this shattering coefficient function for the the very worst case, which is the case in which all points are not collinear, or all 3 points are not collinear among themselves. What is the problem here? When I take a particular problem instance, that's not the case. When I consider, for example, I'm going to learn MNIST, or I'm going to learn CIFAR or COIL, or any other, like I'm going to use like VGG16 on ImageNet, or that's not the case. Why not? Because my data space has somehow similarities, has somehow regions that collinearities happen. So my shattering coefficient function, if I consider this idea by Vapnik, I will have like such a far bound to measure the complexity of my learning bias. That's just unfair in terms of my problem. Why it is unfair? Because it's not representative of my data space, of my problem instance. So here comes our approach. Our approach is quite simple to understand. I think it's like using pictures, it becomes simple, yeah. But of course, there's some math behind. Consider we have like positive and negative points in R2. The whole idea is, what is the distance, the closest point from a different class that I have for every point in my space? If my point here belongs to the positive class, what is the closest negative point from it? It's going to be this one. What about the other 2 points? Also this one. What we do is we build up open balls. Open balls actually helps us to represent topological spaces. So we create an equivalence relation here. What is an equivalence relation? It's just a set where I tell like this point P1, P2, and P3 are similar among themselves because there are open balls connecting them like this, like we see over here. Of course, we're going to do the same with the negative points. So we're going to create a homogeneous positive region and a homogeneous negative region. Consider I have this particular problem, and again, I receive more positive points and they are around here, and more negative points and they are around here. Just like a Gaussian, a bidimensional Gaussian function. So I have like more positive points just always around here and negative points always around here. How many homogeneous regions I have? Just 2. How can I measure my shattering coefficient considering like so many possibilities, considering that every point in my space could be detached somehow from the others if I just have two homogeneous regions? It's just unfair in terms of the complexity of my data set. So what we did was basically, after computing those homogeneous regions, we used a result by Harpeld and Jones, which was actually published this year in February, I think, about separation of points by lines. Actually, separation of points by hyperplanes. It doesn't matter the dimension you have. So those two guys came up with a very important contribution in my point of view, which is how to compute the separability of points in a given space. But their points are points without labels. Just a bunch of points. How can I detach every single point from the others? It doesn't matter the class, because they don't consider class. It's much more like a clustering problem. So how can I detach one point from all others? So that was their idea. And they came up with a lower bound for the number of hyperplanes we need to shatter that particular space, and an upper bound for that particular space. What is interesting is, if I increase the number of points here, of course, I need more hyperplanes to separate every possible point from one another. And of course, I have a lower bound and an upper bound. What we did was basically this. We just took advantage of those two bounds, and instead of applying my sample size n over here, we decided to apply a function, f of n. What is this function about? This function measures our ability of shrinking my data set into homogeneous class regions. So instead of having like a bunch of points here and a bunch of negative points here, consider all those positive points could be represented by a single homogeneous region, and here by a single homogeneous negative region. So I have just two regions to segment, to shatter, to separate, because of the complexity of my particular instance. So we came up with a way of estimating this function based on topological analysis. And from that function, of course, we can estimate the number, of course, after having the number of hyperplanes for the best case and the number of hyperplanes we need for the worst case, I can just power, like two powered to this this number, like the small number and the large number, and I will have the number of regions that I need to cut my input space for the best case and for the worst case. So I have the number of regions. What is the problem now? If I have just two regions like this particular example here, the problem is like a problem of coloring a picture. So if I choose like red here and blue here, or if I choose like red and red or blue and blue, I could just decide on the colors, and colors are classes for us. So after creating all those regions, we came up with this formulation based on combinatorics to decide on the number of possibilities we have of coloring up all those regions that we have in our case, in our space. And what is interesting is, before this, there was no solution for the shattering coefficient of a non-binary problem. And this is actually a solution for any problem with C classes or C labels. So we can come up with this upper bound, and actually there is a lower bound over here for the shattering coefficient function. This is another way of representing the number of functions I have in my algorithm bias, the shattering coefficient function. We call like this. Actually, this is much more common than m. So here I just substituted by n of f of 2n, which is the typical term used in literature. And what is interesting here, just about the contributions, so we can discuss more, we can answer questions. You guys probably have like different ideas, and that's going to be like that's going to enrich the discussion, of course. So over here we have a sample size that goes from 1 to 500, and of course here you can see how we can shrink our space into homogeneous regions. For example, here I have a homogeneous region belonging to class 1, here belonging to class 2, here belonging to class 3, and maybe we have a class overlapping. Of course, if we have a class overlapping, maybe there are like 2 points belonging to the same class that somehow could be detached together. But sometimes that's just impossible. Sometimes there is a single point that is somehow like flanked by other points belonging to a different class. And of course, that's not shrinkable. And what is interesting here, I was just performing an experiment, like increasing my sample size with 2 bidimensional Gaussian functions having some sort of class overlapping. As you guys can see, when I increase my sample size, my ability of shrinking is somehow limited because I have, of course, this overlapping region. So when I have like 500 points in my space, or that's my sample size, I have like 60 regions. What is interesting about this regression, this linear regression on top of my experimental analysis, is that this regression tells me, actually, the slope of this linear function tells me what is the complexity of my data space. If the slope is 0, complexity is 0. If this slope is very, very steep, of course, as it gets like steeper, of course, my complexity increases. What is interesting as well is, let's say this, actually in this case, it was like 0.1, the slope. If the slope is 0.1, my accuracy, my maximal accuracy is actually 1 minus 0.1, is 0.9, is 90%. So we can derive the maximal accuracy from this study as well, without employing an algorithm. That's quite interesting, isn't it? Another point, after getting all those regressions, here we have like some examples of those regressions. Take a look for MNIST, some examples. What is interesting, those regressions, they describe our ability of reducing my space into class homogeneous regions. What is interesting here is this. Just consider, if I consider a convolutional mask or convolutional kernel in my first layer of my, let's say I'm using a CNN, and the first layer considers like masks, 3 by 3 masks, or 5 by 5, or 7 by 7, or 9 by 9. What is the best? Of course, in this case, it looks like 9 by 9, right? Why 9 by 9? Because I can shrink much more my input space. So I can decide on how to come up with nice embeddings, data embeddings for my problem. Another interesting contribution. After having a good estimative or a fair estimation of my scattering coefficient function, I can use the generalization bound. The generalization bound tells me if my expected risk or my risk, when I have, like, without having access at this point to every possibility for my problem, how can my particular classifier F that has a given empirical risk in my test sample, for example, how it's going to behave when I apply it on unseen data. That depends on my scattering coefficient. If my scattering coefficient is not that like large, of course, it behaves like a polynomial function, but a very bounded polynomial function, this is going to be small. You know what is this? This is the variance term. You know what is this if we carry on asking? This is the variance term considered in the Tikhonov regularization. You know what is this? This is actually the variance, or let's call it, let's use a different name. This is the regularization term we use in deep learning, for example. So we can decrease the importance of this regularization just because we have less possibilities in our space of demisable functions, so we can converge faster and easier to the best as possible function inside my bias.
Rodrigo, sorry,
Last,
I'm gonna drop
oh,
you.
sorry.
We're already at a full hour, so just to
Okay.
remind, because people might leave.
Oh yeah. Oh, actually, this is the last slide.
Okay.
So
Thank you.
just the last slide, guys. Here we are increasing the sample size up to the maximal sample size for NEAST using convolutional kernels like 3x3 kernels, 5x5 kernels, 7x7, and 9x9. What is interesting here? If we consider all those kernels and we increase the number of hyperplanes, so we are just increasing the number of hyperplanes to understand how many hyperplanes we need at the first layer of a CNN. You guys can see that if we use a 3x3 kernel, that's going to be a triangle. So we're going, as we increase our sample size, we need more hyperplanes. That's not good, because if I need more hyperplanes, that means somehow my space is increasing in terms of complexity. Not good at all. What if I consider 5x5 masks? That's a plus sign. As you might see, the plus sign is over here. That's the best solution in terms of the number of hyperplanes. You can see that around, actually, less than 60 hyperplanes at the first layer are enough to learn my whole data set, my whole NEAST data set. If I decide to use this maximal number, what happens if I use the maximal number? The maximal number of hyperplanes for a given problem, I tend to overfit data. So it is always better to choose at least one less that number, because of course that gives that just increases the possibility of actually avoiding overfitting. So this is interesting in terms of analyzing a data space, understanding how many hyperplanes we need as we increase our sample size. Finally, here we have, you guys have access to this paper. I hope it is interesting for you guys. It has like all details, everything. And you know, there is an R package I wrote that just performs all those analysis in your data set. So you just provide your data set and it's going to bring something, it's going to provide something like this. I don't know if you guys can see here, but there is, yeah, probably. So this is the analysis after this package. It's going to show me, okay, this is your data set. This is your ability of reducing your data set into homogeneous regions. This is the number of hyperplane you need in the best case, in the worst case, to address your particular problem. Of course, this is the scattering coefficient in the best case. This is the scattering coefficient in the worst case for your problem. Here given 3 classes because we are considering iris. And the 2 functions, scattering coefficient for the best case, for the worst case. Just like larger just to see, it's going to be easier to analyze and whatever. And the generalization bounds being analyzed over here. Guys, that's almost all. Yeah, that's all. Thank you very much.
Okay, thank you. Thank you, Rodrigo, for this kind of in-depth introduction. I guess this would be awesome. It will be kind of nice to have it as part of our kind of, let's say, I can see it for students, like introductory course. Thank you. Because we don't have much time, I see one question. If somebody in the audience wants to ask another question, I could unmute you and you can ask. So I will just ask the only question which is posted. Is the shattering coefficient function, is the shattering coefficient function changed by the characteristics of the model? Example, number of layers in neural networks.
It changes drastically. For example, just consider a single layer of a deep model. Of course, if I add up more units, it's going to change. It's going to be more complex. If I add up more layers, that depends. That actually depends. It depends on the previous layers and how you're mapping from one layer to the other. There is a way of just counting that complexity. But just let's give an example. If I have a single layer with 5 neurons, and I just decide to add a second layer with twice like just 5, 10 neurons. So in the second layer, it's going to increase a lot, actually, our complexity. Yeah, that happens. Very interesting, actually, that question. Very important, I'd say so, yeah.
Thank you. I'm just thinking, this is not my question. What actually this means practically? Because I see people would calculate this bounds and stuff, but what actually that means practically? I see the theory, but how this translates in practice, yeah.
Yeah, before that, we didn't have like any practical result. You're right. That's where I've been working like for the last 7 to 8 years, just to come up with this like very tight way of measuring, of estimating the shattering coefficient. Because after having that, what can I do? I can, for example, just to give like this very interesting idea, if I use this embedding, I can analyze embeddings. That's one of the points. I can analyze how effective an embedding is. I can analyze, of course, if I add up more layers in a deep model, I can understand how effective a given layer is. That's another point. I can understand why 1 minus this slope gives me what is the accuracy, the maximum accuracy I can get from this space. That's also interesting, without running, without like analyzing like forever. Another important point. Many people have been considering deep learning models, but without like any care. People just decide, I'm going to use like 1,000 units in the first layer, 2,000 in the second layer, and so on. What is the problem? You're going to get like a good result, but you have no idea about what is your variance. Your variance is going to increase a lot. What is the effect of that? Of course, if you decide to employ your model in real world conditions, you're going to get like terrible results. I'm sure you're going to get like, that's what people have been showing with GANs, or also with overfitting, especially using deep models. And something else, that's my perspective. On top of this, I've been writing a different algorithm that, instead of learning from data and adapting the hyperplanes, it gives already the best solution. So you get all those, it's an ensemble-based model. You're gonna get all those regions cut from your space. After you just provide like validation data, it's going to prune your model, such as a tree. It's going to remove some of those classifiers, and you're going to get finally a model combining all those local classifiers. That's the final solution. That's what I expect to have. Like, actually, I just wrote a version, actually. I hope to share it with the package probably in 1 week or 2.
Okay, thank you. Thank you
Oh,
for your
thank you.
detailed answer. So any other question? Last question from the audience. I guess we have 2 more minutes. We can round up to 11:10. If not, I don't see anyone raising hand or something. Okay, then thank you all for coming. Thanks once again, Rodrigo, for
Thank you.
being
Thank
our
you.
guest.
Thank you for the invitation.
Yes. And thanks for University of Waikato Machine Learning Group also joining this event. So for all of you, yeah, have a nice summer holidays. Or I don't know, Brazil is also summer, yeah? It's not really winter.
Yeah. It's summer. So yeah, like New Zealand.
Good. So see you then in the new year with new exciting contributions. Yeah, maybe the algorithm you just explained.
Oh, thank you. Thank you.
Yeah.
Thank you. Thank you very much. Thank you again, guys.
Thanks.
So
Thank
bye-bye.
Bye-bye. Bye.